So, we have so far seen quite a few techniques, what is a physical principle and what is the essential difference between them. Now, we move on to another interesting optical technique, which is the method of caustics. And what I want to mention here is caustic is the envelope of light rays reflected, that is what we had seen earlier in the beginning of the course. It can also be refracted by a curved surface or object or the projection of that envelope of rays on another surface. So, what you see here is I have a caustic by reflection, I have a teacup, and because of this curved nature and with appropriate lighting, light hits on this curved surface and gets reinforced, and you see a silver line as a cusp. This is by whatever the line that you get, the principle is called caustics. The same name is also given to the optical technique, we use it for measuring high stress gradient problems, but this is the physical principle. And when you go to a pond, you may also see a nice structures like this, and all these silver lines, what you see them, they are all because of the phenomenon of caustics. Now, you can go and say you might have noticed it, but you may not have named it. Now, you can go and see these are all nothing but caustics. So, caustics is seen in a teacup or on the surface of a pond. What is its use for me in stress analysis? See, if I have to use I mean there is joy in looking at all these patterns and name them as caustics, but I must also have its utility from the stress analysis point of view. How it is seen, we will have a look at it, we will also elaborate upon it. First, we will look at the what is a principle, and this is what is shown here. I have a aluminum specimen which has a crack, and you see a dimple formation here. First, we will see this, then look at the reason behind it. Can you see the dimple very clearly at the tip of the crack? You see a very large deformation here, and this occurs when I apply load. When I this is in 3-point bending, when I apply the load, I have a dimple formation. So, what you find here is when a plane specimen under in plane loading deforms, the thickness of the specimen changes due to Poisson's effect. If I do not have a crack, I would not see the change in the thickness very prominently. Because of the crack, which is a high, introduces high stress concentration, the change in thickness is also very significant, and that is seen as a dimple. So, in this is particularly seen in zones of high stress concentration, the effect is pronounced. And when you look at here, when I send a collimated beam of light, I can have a transmission arrangement as well as a reflection arrangement. If I have a transparent model, then it behaves like a divergent lens, and the light rays whatever I send, it gets deflected, and it forms a particular pattern on the screen. Now, you relate what causes the deviation of the rays. By relating these two, you will be in a position to find out what caused this change and hence the level of stress concentration. So, that is the basic principle behind it. As I mentioned earlier, it is applicable to transmission as well as reflection modes. The reflection arrangement is suitable for studying metallic specimens. This also I have said that you need to have techniques to find out for models as well as prototypes. Photoelasticity has transmission photoelasticity and reflection photoelasticity. So, in method of caustics, you can do it on transparent models as well as on opaque metallic specimens, and particularly in fracture mechanics, when people wanted to understand the plastic deformation at the crack tip, caustic really helped. and it really helped for people who know a little bit of fracture mechanics, establishing the concept of HRR field, Hutchinson, Rice and Rosengren field near the crack tip was very well established with the method of caustics. And what I will do is I will elaborate this aspect of the specimen becoming a divergent lens. We will have a look at it, and this I am going to the chapter on caustics. I will just show you how this deformation is recorded. So, this is the specimen I have a stress concentration here. I pull this model, and from this you know it is exaggerated that you see a thickness change very prominently noted near the stress concentration. Stresses alter the optical properties of a transparent body. You will also have change in the refractive index. If it is a metallic specimen, there is no question of refractive index getting changed. The thickness change because of Poisson effect is very prominent near the stress concentration zone. And if I use a transparent model, most of the transparent models which we use also birefringent. So, the refractive index also has an influence. So, the combined influence of this causes the formation of caustics. So, what I see here is I have an incident ray and it gets transmitted, it does not go straight, it gets deflected, and because of these changes, when I send a beam of light, I will get a shadow essentially behind the specimen in transmission arrangement, and on the reflected this one you will see it on this plane, and you have certain parameters, you do not have to worry about them now. When we go into mathematical development, which we may not do in this first level course. So, you have to take those parameters appropriately, and here again you have shown for a transmission arrangement this is very clear. For the reflection arrangement, you have this dimple very prominently seen. So, when I send the ray, it will get reflected like this, and because of this you will have a family of rays emerging, and that forms a shadow. And if possible, I will also illustrate it by a simple experiment, but before we go into the experiment, we will also take a specimen with crack and make a very simple sketch of it and look at what happens. I will just show that animation for a minute, then we move on to the experiment. And this is very formation of caustics is very clear. Just observe the specimen. So, what I have here is I have a specimen with a crack, I have parallel beam of light impinging on the specimen, and because of the Poisson ratio effect, the light does not go straight. If I do not load the model, the light will go straight, and light gets deflected like this, and because this gets deflected, you get a shadow region on the screen, and you have reinforcement of these rays form a silver line enclosing the shadow line. Because that is found because of the principle of caustics, you call the entire methodology as method of caustics. It derives the name from that. So, you have a family of rays which reinforce and give you a silver line. Is the idea clear? And what we will do is you can actually illustrate caustic by a very simple experiment even in the lecture class. And what I have here is I have a polyurethane specimen, because this I can stretch easily, and I have a crack. I do not think it is very clear, maybe I will put a white background. I will put a white background. You are able to see the crack here. You are able to see the crack here, and I do not know whether the camera is good enough to show that if I stretch it, I will see a dimple that is getting formed. I will get a dimple being formed at the crack tip. Even visually you can see, you can have a dimple formed at the crack tip. When I pull it, you will see the dimple, and if you are not able to see the dimple, we will send a laser beam of light and then find out what happens. Okay. So, what we will do is, can I have one person come and help me? So, what I have here is, I have the model here and I send the laser beam of light, it is not loaded, I see that as a point. You just load the specimen and you will find that the rays are getting deflected. The rays are getting deflected. The rays are not going, because I am just doing it with hand, I am not able to show you the shadow completely, but this is what happens. You are able to see that the rays are not going straight, but that they get deflected. And if you come here, if you look at the sketch again, what you have here is, you have this stress concentration and rays get deflected, and if you actually perform the experiment, you will get the shadow like this. We will have a look at it. Just in a moment I will show you this. And this is caustics is shown for different problems of stress concentration. It is a semi-infinite plate with a concentrated load. This is a plate with a hole, you have a figure of 8, and this is a plate with a crack. I have the crack here and I have a caustic envelope like this. So, you have a shadow bound by a silver region, and you can see very clearly I have a shadow, this is bound by a silver region, that what you have, and this is the caustic shadow for a mode 1 crack. So, you send a beam of light, you get a shadow, you do not get light pass through, and that is mainly because you have the specimen behaved in a fashion where you have thickness change. So, the whatever the light rays impinged on it, it diverged, it behaved like a divergent lens, and you do not have light here, and that becomes a shadow, and that is what you see in the screen. And this is what I try to show, and in fact, you can do it if you do it very carefully, you will be able to see it, because hands are shaking, you are not able to see that in the class. And so, it is a very interesting phenomena. So, what you will have to keep in mind is, if people find out a physics, they are waiting to exploit and develop a new technique, and this has found very good application in the early development of fracture mechanics to establish HRR field. This was a very ideal technique. So, in this class we have looked at how caustics is employed to reveal high stress gradient information. It is not a general purpose tool. If you use image correlation, it is a general purpose tool. If you use photoelasticity, it is a general purpose tool. If you use strain gauges, that is also a general purpose tool. The moment you come to caustics, it is particularly sensitive to high stress gradient information, and I have shown the caustic shadow for 3 problems. One is for the semi-infinite plate with a concentrated load, plate with a hole, and the third one is plate with a crack stretched. Thank you.